It's Super Bowl weekend, but we got a lab to do. Go 49ers, and welcome to Lab 2. Alright, so this lab is basically just a continuation of Lab 1, with the main goal being to compare the electric force from the point charge model of the floating tape in Lab 1 to a line of charges model that we will present here. Now, what do I mean by line of charges? Well, we're going to divide the tape from Lab 1 into multiple segments and treat each segment as an individual point charge. I'm going to be using GlowScript as the computational model to simulate the tape and its interacting forces. And here's just a quick rundown of the results from Lab 1 and the results that we will gain here in Lab 2. All right, now for the fundamental physics principles, and these are exactly like the ones I used in Lab 1. First up, we got Newton's second law, which says that a system's change in momentum is proportional to the net force applied. Coulomb's law, which describes the force of attraction or repulsion between two electric charges. And lastly, gravitational force, which describes the attractive force between two objects with mass. And these principles will help us with our calculations and understanding of the lab. So since we're going to be comparing the line of charges model to the point charge model used back in Lab 1, here I've listed and displayed the main results that I gained back in Lab 1. To the left is all the initial conditions and the dimensions of the piece of tape. And to the right is the computational model. And there I've displayed the system, which is the top floating tape, and the surroundings, which is the bottom tape. And in yellow, I've highlighted the charge on the tape that we were able to calculate from the point charge model. Back in Lab 1, I went through 3 major steps to find the total electric charge that was on a piece of tape due to the point charge model of electric field. Well, now using the line of charges model, we're still going to go through the same 3 steps. First, we'll determine the gravitational force acting on the top floating piece of tape. Then we'll set this equal to the electric force, since those are the only 2 forces acting on the stationary piece of tape that is floating in space. Then we're going to be using the electric field of a rod in order to isolate for charge and find its value. Now, why are we using the electric field of a rod? Well, the bottom tape is, again, segmented into tiny point charges along its length. So that basically acts as a rod of point charges. All right, the moment we've all been waiting for, the computational model. First up, I went and specified all my constants and initial values. These are the 2 main functions I'm going to be using in the computational model. The top one actually creates the electric field itself, whereas the bottom one creates the line of charges. Now, how does it do this? It does it through that for loop you can see at the bottom of the code. Basically, we're taking the length of the tape, or rod in this case, and splitting it up into n different segments. In my case, I used 50 as n, so 50 different segments. And each of these segments represent a point charge with a specific amount of charge and mass. And each of these point charges are going to be used to create an electric field on the top floating tape. Superposition. Side note, I recommend y'all listen to Superposition by Daniel Caesar. Amazing song, although I highly doubt he's talking about point charges and floating pieces of tape. But anyway, how am I going to be using superposition in this lab? Well, remember we took that top tape and split it up into 50 different segments of point charges. Well, in this code, we're going to take that bottom piece of tape and calculate the electric field at each of those different segments of point charges. Well, since there's so many different point charges, we're going to be using nested for loops to iterate through the whole process. All right, now for the grand finale of all that code, here we can see the graphical representation of what all that code even did. You can see those 50 green arrows that represents the electric field from that blue bottom tape acting upon those point charges on that red top tape. And at the bottom, you can see the magnitude of the electric force and the gravitational force, and they're calculated to be about the same, which makes sense since our tape is floating, so that means the forces should balance. In this lab, I made a couple of assumptions, such as assuming that air resistance and friction are negligible, each piece of tape had the same amount of charge, and that the charge on each tape is uniformly distributed along its length. Now, some possible errors that I could have made throughout the lab is that the measurements were not exactly super precise, and also there was a loss of charge due to handling and the outside environment. Now that we've successfully completed Lab 1 and Lab 2, we can finally compare the results. Well, let's answer this first question. What if the tape was treated as a point charge? This is exactly what we did in Lab 1, and as you can see, there's quite a difference between the charge we calculated in the point charge model and the line charge model. Well, why do these estimates differ in the first place, and which is closer to the real value? Well, these estimates differ due to the different levels of precision used in calculation. And it would make sense if the line charge model is closer to the real value because it uses smaller segments of point charge along the tape's length, whereas the point charge model generalized the whole length into one singular point charge. As always, thank you so much for your attention and have a great day.